Alright, welcome to AP Video 15.5. This is going to be on calculations of a strong titration. Main goal is to be able to calculate pH at any point during the titration, whether at the beginning, the end, or in the middle. Understand what the equivalence point is, and when we're all done, we'll analyze the titration curve and point out some important features of it. So when we say strong titration, we refer to a strong acid being titrated by a strong base, or vice versa. The first word, when we say strong, or next video we'll say weak, strong, the first word is always the analyte, what we're going to analyze. The second word is always the titrant, what we have in the burette and what we're trying to analyze. We analyze the analyte with. Okay. Anytime we do a strong titration, what we really care about is the net ionic equation. So let's pick our two favorite strong acid and base, which is hydrochloric acid and sodium hydroxide. So here we have the molecular equation where everything is present, and we produce water from this, and the other double replacement reaction product is NaCl, a salt. Anything that's aqueous we can split apart, so strong things are aqueous and they ionize completely, same with the strong base. And then this is a soluble salt, so it also breaks apart. And what you have here is spectator ions. Sodium and chloride are spectators. So the net ionic equation is H plus OH minus makes H2O. So all strong titrations have this for their net ionic equation. And this is what we're going to put into the Rice table. This will end up being the R that we write down for the reaction. Okay, so strong means a strong acid and base are being used in the titration. Now, when you use your Rice table, because we're adding an acid to a base, it's all about stoichiometry. So what you need to do is do the stoichiometry in moles and basically figure out what's left over of H plus and OH minus. Typically one of those things is left over. There's one point where they're equal to each other, that's the equivalence point, but every other point in your titration, one of those two things is going to be left in greater amounts. What you need to do, and is really important, is you need to divide by your new total volume, because when you add the titrant up here to your analyte down here, this volume is essentially constant, so you have a starting volume, and every time you add some base, that's some volume you're adding to it, and you always got to divide by the new total volume, which is those two things added together. So keep in mind what your new volume is as you go through the titration here. You should pick up the Titration for Dummies handout in class. Make sure you kind of follow along with that when I go to that. And we're going to, now in the next problem here, do a titration calculation. And it says in class here, but we're going to do in the video. So, one of the number one things you need to figure out is, what do I have? Always ask yourself that question. What do I have? Because knowing what you have is really important for how you're going to calculate the pH. So on this one it says we're going to perform a titration by adding 0.6 molar potassium hydroxide, and hopefully you recognize that potassium's a neutral ion. We really don't care about it. We're adding strong base to 40 milliliters of HCl, and it's 0.8 molar HCl. And for strong acids, it's really just the H plus there that we really care about. HCl is our analyte. Now typically, like I talked about in the previous video, you're not supposed to know the concentration of your analyte, but in this case here, we're trying to learn how the titration curves work. So we know pretty much everything in our calculations, so that way we can kind of compare it to a titration curve. So here we go. It says calculate the initial pH before anything has been added. And that's really important, because before you add anything, the question is, what do I have? Well, the only thing you have before you add hydroxide is a solution of HCl. So at this point right now, all we have is 0.800 molar HCl. This is a strong acid, so therefore this is the concentration of the H plus ion. And from that, we can find the negative log and find pH. And the pH, when you take the negative log of 0.800, is 0.097. So that's the pH for our starting amount here. Okay, I'm going to go to the Titration for Dummies thing here quick, and you should as well. Go ahead, and if you have two different highlighters, that's great. Otherwise, if you just use the same color, that's fine as well. Right here. So the way a titration curve works for a graph is pH is on the y-axis, volume of your titrant is on the x, and we've added 0 volume of hydroxide. So initially, before the reaction starts, so this first green line here, I'm going to scroll down now, and you can pause the screen to write this down, but initially before the reaction starts, your starting pH depends on the type of acid or base you have. It depends on if it's a strong or a weak acid, in this case a strong acid. And how do you calculate the pH of a strong acid? This is a chapter 14 question. Always go back to what do I have and just do your calculation based on the type of problem you're supposed to calculate with. Okay. Go ahead and draw another yellow line right where the vertical part is, and draw it vertically down to the volume here. And just so you know, this particular curve is based off a different practice problem, so they're not going to be the same numbers as we do the calculations here. But in general, where the vertical line is right here and it goes down to a volume, that particular volume there is what we call the equivalence point. At this particular volume, you've reached the equivalence point, and that's the moles of when the acid and the base are equal to each other in concentration. And for a strong titration, we'll find out the pH is 7, because when those two things are equal to each other, they've neutralized each other completely, and you have pure water, so it's pH of 7.00. Okay, and we'll come back to the rest of this in a little bit. Alright, so now we're going to add. Now in your notes, I would like you to draw a line in your workspace here for letter B and split it in half. Okay, so now we're going to calculate the pH after the addition of 10 mils. And we'll do this on the left-hand side of the line. Okay, now I'm not going to draw a line, but on your left-hand side here, we're going to do with 10 milliliters. Now when you add base to acid, it becomes stoichiometry. Okay, now when you add a base to acid, it's really about that rice table, and the reaction we're going to work with here is the net ionic equation. The H plus from the acid reacts with the hydroxide from the base, and they're going to form water. Now if we're doing stoichiometry, we have to be in moles when we plug those numbers in here. Okay. Now here's a new one for you. It's called the millimole. Okay, we're used to molarity being equal to moles per liter. Well, it turns out when we calculate to moles by using these numbers here, our mole number is going to be some decimal number. So let's just do one of these really quick. So I'm going to convert the 40 milliliters to liters, and in liters that's 0.040. I'm going to multiply that, so molarity M times liters, so 0.04 times its concentration of 0.8. Okay, the acid here, 40 milliliters, and that right there ends up being 0.032 moles. Okay, that's what we could plug in here. Now there's a new thing we call millimole. So if you put a little m here, millimole divided by milliliter, well, the millis technically cancel out and still make molarity. So another thing we can do is kind of rearrange this equation here. Multiply these two things together. Milliliters times molarity equals millimole. And if I do the exact same thing here now, but I'm going to use 40. 40 times the concentration of 0.8 here ends up being 32 millimole. And the biggest reason we use millimole in our titration calculations is because it's not very fun to add and subtract decimal numbers like this. 32 is a lot easier to work with. So, and this is going to be a constant now because our acid is 40 mils, this concentration, so we put 32 millimole here. And for the hydroxide, its initial amount is 10 milliliters times its concentration, and 10 times 0.6 is 6. So we have 6 millimoles of hydroxide. Water, we don't care. And now the change is, whichever one's the limiting reactant, you subtract it. So here's your limiting. So you subtract 6 from both of these, and we get 26 millimoles of H plus left, and this is gone. It's been neutralized. So at this point, this is how many millimoles of H plus are left over. Well, to calculate the pH, we need concentration. So we have to get these millimoles back into a concentration, which means divide by volume. Alright, so the total volume is, again, what you've added. So it's 10 milliliters plus the 40 milliliters we started with. So if you add those together, our new total volume, VT, is equal to 50 milliliters. Okay, so we're going to divide 26 by 50 milliliters. Millis technically cancel, and we're back into molarity. So 26 divided by 50 is 0.52. So right now our concentration of H plus is 0.52 molar, and from that we can find pH. So take the negative log of your concentration, and you get a pH of 0.28. And if you take a look at our original work here, we start with pretty much 3 sig figs and everything, so I should probably go a little bit further. So 0.284. And that's the pH of our solution. Okay. Now what I want you to do is I want you to practice doing one on your own here. So on the other side of this line you had drawn, I want you to pick any number that's greater than 10, so it's got to be basically 12 to 50. I want you to pick any even number between 12 and 50 for the amount you're going to add here, and do the problem again now. And then when you're done, I'll have a list of answers here you can check and see how well you did. I have every answer between 12 and 50 you can check your answer with. So go ahead and pause the screen and see if you can do the calculation with a new volume there, and then check your answer. Okay, so I put together an Excel spreadsheet that helps me calculate all this information really quickly. You picked some number between, for your base, 10 mils, or 12 mils, excuse me, all the way to 50. So here's your possible choices. I kind of have them highlighted right here. Okay, and as you go across over here, the green spot should be the pH you calculated. So if you picked 28 as your milliliters you've added of base, the pH you should have calculated is about 0.65. So go ahead and pause the screen, find your answer, and see how well you did there. Okay, and going back to this now, so essentially when you're adding acid to base, it's about get into millimoles of the two things. It's the stoichiometry, and we're neutralizing, and we don't care about water here. Figure out how much is left over of one of the two things, and divide by the new total volume. So make sure you divide it by whatever volume you added, plus the 40 mils of acid we start with for a solution. Okay, up next we have still our same thing we're working with. Now we want to know how much volume of base it's going to take to reach the equivalence point. Well, what's equal at the equivalence point in a strong titration is the moles of H plus are equal to the moles of OH minus. Or another way to think about it is the millimoles of H plus are equal to the millimoles of hydroxide. Well, if we have 32 of these, we need 32 of those to be equal to it. So we know we need 32 millimoles of hydroxide. Well, if we divide it by its volume, or not its volume, by its concentration, we can get the volume we need. And when you divide millimole by molarity, you get milliliters. So 32 divided by 0.6 is 53.33 repeating. Okay, milliliters. That's what's required of this hydroxide to reach the equivalence point. Now what's really nice about the equivalence point of strong titrations is that in the Rice table, and you've reached the equivalence point when the millimoles are equal, so 32 and 32. And they both neutralize each other, so there's none of these things left over. All you have is water. And if you have water at 25 degrees Celsius, the pH should be 7.00, and we'll assume the temperature is 25 degrees Celsius. So the equivalence point of all strong titrations is 7 when you reach their equivalence point. Okay, up last we have, well, let me pause for a second. Let's go to titration for dummies. So what we just did was the equivalence point. So I know this volume doesn't match with what we just did, but that's a different problem. But essentially when you reach the equivalence point, you can see that there's this huge increase in pH. That's pretty common there. If you look at my data from the Excel document here, notice how the pH over here rises, and right when you get close here to the equivalence point, it rises very rapidly. Okay, so that's very characteristic of a strong titration. Okay, continue on. I again had more students come in, so I'm not sure what I was talking about. Okay, good. Go back to the titration for dummies. Okay, so at the equivalence point, pH equals 7 for strong acids, strong base titrations. Now everything between the green and yellow lines, everything between the initial and everything and before the equivalence point, everything between there is stoichiometry. Okay, here's what you need to write in your notes here. everything between those spots, so pH between the start and equivalence point and not including those points, is the stoichiometry between H plus and OH minus. Do the stoichiometry and calculate how many moles of H plus are or OH minus is remaining, and make sure to divide by the new volume to get back into concentration. Now, for a strong acid being titrated, the the excess reactant is H plus. If you have to do an opposite titration where you start with hydroxide and you start to neutralize it with small amounts of H plus, this is what's left over. But whoever the excess reactant is here, when you're done with the stoichiometry part, find your new total volume and divide by that to get your calculation. Okay, last thing up in our calculations now is going beyond the equivalence point. So when you go beyond the equivalence point, 5 mils past it, 5 milliliters past the equivalence point would be 58.33 milliliters. Okay, let's just do the rice table now. So the rice table is our same reaction of H plus OH minus. And one thing you should notice here, the initial amount of H plus is always the same. So we always assume we kind of just go back to the starting amount, 32 millimoles. And then 58.33 times 0.6 is about 35.00 millimoles. Okay, so now you can see that the limiting reactant has flipped. H plus is now limiting, and the hydroxide is the excess. So we're left with 3 millimoles of hydroxide left over. So now divide by the new total volume, which is 40 plus the 58, so that's 98.33 milliliters. Milli cancels, we're into molarity, and 3 divided by that, 3 divided by 98.33 is a concentration of 0.0305 molar OH minus. And from this, you'll find POH, and from that, you'll calculate your pH. So negative log of the 0.0305 is 1.516, and then 14 minus that to get back into pH is 12.484. That's the pH as we go beyond the equivalence point. Okay, so going back to titration for dummies, once you go beyond the equivalence point, whatever there is of moles of the excess remaining now, which should be a hydroxide in our example, or if we do the opposite titration, H plus will be left over, divide by your new total volume. It's just a strong acid or base left over. Find pH or POH respectively to get to your eventual pH. So this is what the titration curve of a strong always looks like. It has this shape to it. So here's one version. The problem we're doing in our practice right now looks like this. Okay, kind of stretched out a little bit differently. And we need to graph that now on your sheet. So if we kind of graph it, let's put a pH on the y-axis. We'll start here at 0. This is 14, and right in the middle here is 7. And our volume added, this is the volume of base added in milliliters. And we went from basically 0 to 60, so we can go 10, 20, 30, 40, 50, 60. Okay. At 53, go back in my slides here a second. At 53.33 milliliters, that was the equivalence point, so that's a pH 7. So right about here. Then we started about here, and at 10 milliliters we went up to about this pH. And I might be off a little bit here, but essentially it has this kind of shape. It goes really slow increase, and right before it gets to the equivalence point, it skyrockets through here. And then our ending pH was 12.5-ish, which is right about there. And it goes up and levels off like this. So all strong titration curves have this shape. So here we can look at 3 of them, or 2 of them. Here's the one that we just did. And titration for dummies, you can see it has basically the same shape to it. Okay. Things you need to know about this for characteristics. The equivalence point is where the large increase takes place. The midpoint of this large increase is where the pH is at the equivalence point, so it's pH 7 at this equivalence point. It just gradually increases. It eventually skyrockets and then levels off. Okay, so let's go back. So characteristics. Gradual increase, and stays gradual for quite a while, stays gradual, and then sharp increase at equivalence point, and then levels off. That's kind of the characteristic of a titration curve of a strong titration. Okay, so good luck with this, and we'll do some practice problems in class the next day, and then we'll move on to weak strong titrations, and those are a little more difficult. So let's make sure we nail these ones first before we move on to the harder ones.